Okay, so I'm also from SA, from University of Adelaide at the WAIT campus. So today I'll give an update on the frost tolerance research that we're doing there. So I guess one of the major constraints in frost research has been our lack of capacity at a national level to measure frost damage. And obviously if you can't measure frost, well, it's difficult to improve. So starting in 2012, there was a new program started called the Australian National Frost Program, and that's a partnership between GRDC, the University of Adelaide and DAFWA. And this is basically a national frost screening facility. We've got 3 nodes in each of the growing regions. So we're based up at Loxton in SA, Merredin in WA and Narrabri in New South Wales. And each of these facilities, basically people can submit in germplasm to be tested, and results will be coming back out based on frost susceptibility. So to go along with that, we've developed a set of standardised protocols that are used across all these sites, and that includes weather monitoring and a range of other environmental characteristics that we look at. The trials themselves are designed by SAGI, the GRDC run statistical program, and they also analyse the data. And we have an advisory group comprised of the GRDC researchers, growers and breeders to oversee the running of the program and what it's actually doing. So last year was the first year that this was operational. So we're obviously doing field-based frost screening, so we need some pretty cold sites in which to do our testing. So this map here shows the potential frost days, potential days below zero, based on 30 years of historical data. So you can see here we're in some of the colder parts of the wheat and barley growing regions, which is what we need. So this is just looking at the Loxton weather patterns here. So we try and sow our trials so that they're flowering within this window from mid-July to mid-September. So flowering's the most susceptible stage of development in wheat and barley, so we try and target this window. To do that, we use about 7 to 8 times of sowing, which are spaced evenly between April to June, to try and target naturally occurring frosts at flowering for our test lines. So I mentioned we have weather recording instruments at each site. So the main thing here we're looking at is canopy temperature to determine when a frost has occurred. And probably something to note here is that at our Loxton site we actually have the Bureau of Meteorology weather station right in the middle of our frost trial, so we can look at that and also compare it to our weather stations. And if you're looking at canopy height, it's generally a couple degrees cooler than what the bomb site's recording. So if you're looking at the bomb site, you might not think you had a frost, but you may have actually had one and are starting to see some damage. So it's something to be mindful of. So we've developed some standardised protocols that we use across the sites. So following a frost, we'll go out into every plot and precisely determine which heads are at flowering. And then from that, we use a morphological template to tag out all the heads in the plot, good proportion that are at the correct flowering stage. And that's important to take out maturity effects from our trials so that we're comparing things at the same stage. We also now measure a lot of covariates within the plots to try and increase our accuracy, but also understand other factors that are contributing to frost damage. And then a few weeks after we've tagged them, we'll go out and hand harvest these heads and take them back, and then we have a team of seasonal workers that sit there and count the number of sterile grains within each floret. And then we express that as % frost-induced sterility. So it's quite labour intensive, but we can get through quite a large number of samples each year across our sites. So this is the type of damage that we generally see. So it's quite obvious in barley. So we sort of get this intermittent sterility in barley. And what we find, this is a very quantitative trait that we see genetic variation for. If you get a more severe frost and you get stem damage and it just wipes out the whole head, we don't see a quantitative nature to that trait, and we don't see genetic variation, but for this intermittent sterility we do. In wheat it's more difficult, you might not even see any damage at all, but there might be a high level of sterility. So we've been validating these methods now for several years in a range of projects. So here's a set of data from a small project we had in wheat. So this was run over 3 years with 3 varieties, young kite and wild catcham. And we've got 10 separate frost events here, and the minimum temperature is shown on the bottom. So using these methods, we could reproducibly rank these 3 varieties based on their susceptibility, with young being the more tolerant and wild catcham more susceptible in this case. But what's worth pointing out is if you have a severe frost, say getting down below -5, everything's pretty much going to get wiped out. We can't stop things freezing like that, but under mild conditions there is genetic variation. So we've also looked, we were looking at larger germplasm sets, so Australian varieties, but also bringing in a lot of international germplasm and some more exotic lines, and looking at benchmarking them. So I'll just, this is a trial from 2010 that we had. So one of the lines here that we've had, which is looking promising in a lot of our trials now, is this Oz 30323. That's a line that we got out of Simmet, and it's a synthetic derived line, and it's got some exotic genes in there from wild wheat sources. So we're quite interested in that now, and we have mapping populations that we're dissecting the genetics of that line and integrating that into Australian material and validating its usefulness. If you go up the other end here, there's some of the lines that Paul mentioned, so things like Sunstate appear quite susceptible. But you can see there's quite a spread of genetic variation there. Similar story in barley. So barley's overall more tolerant than wheat, but we still do see genetic variation. So so a line such as Kill is actually pretty good in the scheme of things. But if you go up here, some of the older varieties, such as Bark and Galleon, actually show a higher level of susceptibility. So these benchmarking trials we're running at Loxton through the University of Adelaide, they've now been formally taken up by the Australian National Frost Program. And what we're doing there is to basically benchmark frost-induced sterility in all current Australian wheat and barley varieties. And this data is going to be made available to growers. We're saying after 3 years of trials to make sure that we get the results right and they're robust and meaningful to you guys. They will come out through the MBT system, very similar to current disease ratings that you'll get for the varieties. And the aim here is to assist growers in managing the risk of frost. So this is a snapshot of the trials that we ran last year. So in wheat, we had 65 varieties that we were looking at. Barley, we had 48. So basically everything we're putting through the Loxton site, that's the biggest frost nursery that we have, and then more regional specific lines are going into WA and New South Wales. But everything's in at least 2 sites, so that we can start looking at genotype by environment effects as well. So we've also, majority of the breeding companies have also come on board with this and given us their soon-to-be released varieties. So the good thing about that, once we get these ratings out in a couple of years' time, they'll still be up to date with all the new varieties that are coming out then. So this is the minimum temperature graphs from our 3 sites last year during the flowering window from July to start of October. So you see, as you're probably well aware, last year was pretty frosty around the country. So in South Australia we had a couple of distinct frost events. Western Australia at Merredin was a little bit milder. There was a very late frost event here which caused some damage in commercial crops. But New South Wales was extremely cold, especially in early August, where they had, I think it was about 20 or up to 25 days of continuous frost every night. So the red arrows here are where we collected data from. So we had material flowering where we collected heads, and in total we looked at around 76,000 heads. So this is just a quick snapshot of the wheat-Loxton wheat data that we got from the Loxton site last year. This is still being analysed, so this is just very preliminary data. But overall we can see the rankings that we got were consistent with what we've seen previously. So the level of damage ranged from a bit under around 10% up to around 40% in this trial. And again we're getting this Oz 30323 line here at the lower end. Gregory is appeared good in this trial and also in our previous trial, so we're a little bit interested in that. But then up here, again, we've got the sun state and, for example, wild catching here with the higher levels of damage. Similarly in barley, so you can see here again, damage in barley was less than wheat, but again, the rankings were consistent with what we've seen with these control lines that we have. So we've got kill here, and then galleon and bark up here. We've also got some international lines here, which actually this one here particularly performed much worse. So there is actually a lot of genetic variation still out there in barley for frost tolerance, but generally a lot of the existing Australian germplasm appears reasonably good. So those the rankings that I mentioned there and all the data that we're generating so far is based on floret sterility to determine what's good and what's bad. But I guess the final question is, how does that affect yield? So there's a new project, I believe it's starting this year, GRDC project, which is going to start to put these frost rankings in relation to yield. So here we have some preliminary data from a couple of years ago that we got from a yield trial that was affected by frost, and we can say generally that a 1% increase in frost-induced sterility reduces yield by about 1%. But as you can see here, that's quite scattered, and we're really interested now in how individual varieties compensate once they've actually been hit by frost. So the take-home messages from this, so really reductions in grain numbers start to occur in wheat at about 0 degrees. In barley it's a bit more tolerant, so say -2, but there may actually be no visible signs of frost damage. But once you get lower temperatures, say -2 in wheat, -6 in barley, you can expect to see quite significant losses in grain number. And under these mild frost events we do see genetic variation, but if you start getting too cold then everything's going to be wiped out from what we've seen so far. What I haven't spoken about much yet today is basically the genetics work that we're doing in the background, trying to deliver genetic solutions for frost tolerance. So that's a lot of what Paul spoke about too, bringing in a lot of international and exotic germplasm, integrating it into Australian lines and trying to identify new sources and genes for frost tolerance. So that's all going on in the background, and then that will feed into the ANFP, and we can basically measure progress that we're making in that regard. So I'll wrap it up there, and thank you.